All right, so now we move on to lesson 2.3, which is dealing with the sine law. And the sine law is a particular way of looking at non-right angle triangles and establishing how we can solve for either angles or side lengths given a certain relationship. Now, to begin this lesson, what we're going to do is we're going to prove this identity that's given on your formula sheet, which is that the sine law relates that we have vertices A, B, and C, where there's angles at A, B, and C, and they each have a side length. And the angle relationship slash the angle side length relationship you're going to be given is this one here on your formula sheet. Now, you're going to notice one thing about this relationship is that this one is just the reciprocal of this one and vice versa. This is the reciprocal of this relationship. And so when we look at this relationship that we're given to on our formula sheet here, you want to analyze it in the following way. Whenever you're given a capital letter like A, B, and C, such as this, anytime we have that capital letter, it indicates the angle at that vertices A, B, or C. When we deal with the lowercase ones, that's going to be the side length that is opposite of that angle in the given triangle. So before we do our proof, what we're going to do is we're just going to set this up in the triangle. And we're going to say, well, if I have a triangle that's a non-right angle triangle that's A, B, and C like this, what we're going to do is we're going to break it apart in the following way. I'm going to, first of all, make a height measure that splits this into two 90-degree triangles. And you're going to see why just in a very short second. But for now, we're going to label this as the height of the triangle. So this is how tall the triangle is. Then what we want to do is we want to label the given sides of A, B, and C. Remember, they're always opposite of the angle, just as mentioned. So I'm going to make this side A. I'm going to make this side B. And I'm going to make this side C. So that's me going across from each of the angles, angle B, side B, angle A, side B, and I do that for each of the sides to indicate which is the corresponding side to the given angle. Now, what we're going to do is in this given proof here, we're going to take this and we're going to be like, well, if we want to label this vertices as vertices D, we're just going to invent a new vertices to represent that when we split this and we create a height, that it creates another vertices, that other vertices is right here. We're going to use letter D to represent that. Now, here's how we're going to prove this in terms of, here's how we're going to generate this sine law. They say in the triangle ABC, draw an altitude of AD and BC. It basically just create a right angle triangle just as we've done as such. And we're going to let this AD, or the connection of AD, be the height measure that is the height of the triangle. Now, in the triangle ABD, or in the left triangle, as they refer to it here, when we talk about sine B means we're going to look from the perspective of B and go opposite over hypotenuse. Well, in this situation, what we're going to do is we're going to say opposite over hypotenuse. That's the same as saying H over C, because C is the hypotenuse on that triangle. And thus, when we isolate for H by multiplying C up, it's going to be C sine of B. Awesome. Okay, so that takes care of the sine rule for our first triangle, or the left triangle. Now, we're going to go to the right-hand side of the triangle, or triangle ACD, which is on the right here, and we're going to do the same thing. From the perspective of C, it's opposite, which is height, over hypotenuse, which is B. So we're going to write this as H over B, and I'm going to just make sure that H is a little bit neater and not looking like an N. There we go. When we multiply the B up to isolate for H, we're going to get H is equal to B times sine of C. And remember, we want to use capitals to represent the angles in here. So just make sure you're using capitals in lowercase and it's very apparent. Now, they say, let's take these two equations and relate them, because if this is the same height we're talking about, the height that splits this down the middle and creates two 90-degree triangles, well, then shouldn't this H be equal for both of them? So what we're going to do is we're going to take the relationships we've just derived and say, well, if H equals H, the two heights are equal, then the C side length times sine of angle B is equal to side length B times the sine of the angle C. And if I manipulate this just slightly, what I can do is the following. I could either divide the side lengths, which in this situation, if I divide by both the side lengths, it's going to become sine of B divided by B equals sine of angle C over C. This is me dividing the two side lengths to each side, because if I divide by B and divide by B, it will cancel from the right-hand side and go to the left. If I divide both sides by C, it will cancel from the left and go to the right. Hence, this is my identity. And then just as we've established within our formula sheet, we know that if I just take the reciprocal of this, the relationship will still hold. Yes, the ratio might be a little different mathematically, but I can take the reciprocal at any point in mathematics and know that if I take the reciprocal of the left and the right-hand side, the relationship will maintain and I should be able to have the exact same thing. So whether we're given the first relationship or the second relationship, I want you to know that both of them are equivalent. There's no difference between these two other than one has the side length in the numerator, the other one has the side length in the denominator. And then we're going to discuss throughout the problem solving when it's better to use one or the other. I mean, technically, you could use either one and get a solution, but in the case of you're given an angle and you want to solve for a side length, I would most likely use this one to prevent against like using a ton of algebra. If you're solving for an angle and you're given both side lengths, I would use this variant here because it's probably going to be a little bit better for you there. All right, so here's the thing. With sine law, we could do this for any of the sides. We could use it for A and B, we could use it for B and C, we could use it for A and C. Regardless of which one we use it for, we're gonna find that the relationship is maintained, that we can have a relationship of the side lengths over its sine relationship equal for all sides. Or we could have the angle with its sine relationship over the side length, and all the relationship would be maintained. So it doesn't really matter which side lengths we're comparing; they're all going to be comparable using this sine law identity. Now, again, we can use this for all of the relationships or all the side lengths and angles. And when we use this, the sine law can only be used when there's an angle and the opposite side is either known or unknown. And this has to occur in a pairing. And what I mean by that is we have to have either two angles and a side length or two side lengths and an angle in order to figure out using sine law what that missing value is. So you'll see that throughout the problems, and I'll make sure to point that out, whether we have side angle or whether we have angle, and side. And this will become very clear in the coming examples here. Okay, let's flip over to our first example here, and it's going to be a bit of an applied one. So I always hate to bring in tons of sentence structure into these problems, but you know, that's part of math, is pulling apart these problems. So Pudluck's family and his friend own a cabin on this lake or on this river in Nunavut, and Pudluck and his friends wish to determine the distance from Pudluck's friend cabin to the shore on the edge of the town. Now, one thing that we need to indicate here is that they're looking for the distance from the friend's cabin to the communications tower, or aka where the store is. So what I would do here is I would just put an arrow down here and be like, this is where they're talking about the store being, because they said the store is basically connected to the communications tower. So we want to make sure that we label this. The other thing we're going to label before we figure this out or do anything more here is we want to label the sides. Angle or side length A is going to be here because it's opposite of angle A. Side length C is going to be opposite of angle C. And then side length B is going to be opposite of angle B there. So this is what I would like to fill in there, and we're good. Now, let's continue the sentence structure here. Now that we've done a little bit of the labeling, we know where the store is. They want to figure out the distance between the friend's cabin and the store, aka this is our end goal, is to figure out what A is. But in order to figure out what A is, they know that the distance between the cabins is 1.8. So that's a piece given to us on the triangle here. The distance between the friend's cabin and Pudluck's cabin is 1.8. Using a transit, they're able to estimate the angles between the cabins and the communications tower that's near that store they're looking for. And as shown in the diagram, determine the distance from Pudluck's cabin to the store to the nearest tenth of a kilometer, aka what is the distance A here? Now, in this situation here, we want to look at, first of all, figuring out what is the pieces of information we're given and do we have enough information to figure out A? And I would immediately push back on this piece here. If you look at what information is given, remember, to use sine law, we have to have a pairing of either two angles and a side length or two side lengths and an angle, but they have to be done in a very particular way. If I look at this, I'm trying to solve for this side length here, the side length A. I know the angle, but I don't know the side length. Obviously, that's what we're looking for. With this side, I know the angle, but not the side length, so that doesn't really help us much. And then I know the side length, but I don't know the angle here, so we don't have enough information. What we're going to use is triangle sum theory from Math 10C to figure out what is this angle here so that we can use this pairing with this pairing to help us solve for A. So let's do that right away here. We're going to go step number 1. Let's use triangle sum theory. Perfect. Now I'm going to use sigma just as a way to represent this sum, because we know that the this symbol here, which is sigma, is the sum of the interior angles, so, or the sum just generally. So triangle sum theory says that they should all add up to 180. And if we have this, then what we're going to do is we're going to say, well, 180, which is the total, is equal to, we have our first two degrees, which are 61 and 88. So 61 plus 88 plus angle C, which I'm going to use the inequality symbol. This is very, very common within this. You use this little inequality to represent it. Well, it's not really an inequality. It's just a angle symbol. Angle C is going to be added to these three, and supposedly that's 180. If we subtract the 61 and 88 from the 180, we end up actually figuring out that the angle at C is equal to 31 degrees. So this is a piece of information, and as soon as you get that piece of information that might help you in the problem, what I recommend is if there's a diagram, then make sure you fill it into the diagram. If there's no diagram, maybe draw your own and then fill that information in, because it might help you here. Now, here's how we know we can use sine law past this point. If we know that we have a degree and a side length that are paired, and we have a degree and an unknown side length, that means there's enough information. We have two angles and one side length that are in these pairings and one unknown. We can then set up sine law accordingly. Now, what I'm going to do is I'm going to get a little bit technical here in the sense that I'm going to write this as the following. For step number 2, because the distance we're looking for is defined by side length A, let's just clearly define what side length A is. So we're going to say, let the side length A be the distance between the cabin and the store. Now, for some of you, you might look at that and be like, why would we even put that in there? The more you go through math, the more technical you want to be in terms of defining your variables, because you don't want to leave people second guessing as to what you're thinking, especially when we're using sine law with just generic variables. You want to be very specific on what you're talking about. Okay, so let's set up sine law according to this. We know that we have the side length A that we're looking for divided by sine of the angle A is equal to side length C divided by sine of the angle C. Now, you're probably thinking, why did we use this variant? The reason we're going to use this variant and not where the sine is in the numerator is I'm trying to solve for A. So if I want to eliminate some of the algebraic steps, why not just start with the side length A in the numerator, and then that will help us out. Now, we want to isolate this A, so what we're going to do is we're going to multiply both sides by the sine of A, or multiply it by the sine of angle A. What this is going to leave us with is A is equal to C times sine of A all over sine C. There we go, and I'm just going to make that a touch neater. There we go. This is equal to, we're just going to plug in some numbers here. So the side length C was 1.8 kilometers times the sine of angle A, which was 61 degrees, divided by, in the denominator, the angle we found through triangle sum theory for angle C was 31, and then therefore this gives us that the distance between the friend's cabin and the store is going to be, to the nearest tenth of a kilometer, 3.1 kilometers. So we want to just include a little sentence, 3.1 kilometers from the cabin to the store. And the reason I'm going to include a sentence is because if I just put in 3.1 and I just leave it at that, it's like that might be a little bit too ambiguous, right? It's like you need to actually have information laid out there. And I know we've defined that A was the distance between the cabin and the store, but if you, let's say, didn't include this let statement, it might be a little confusing of like, if you just throw in 3.1, what is that? Now, again, if you had a diagram, what would really help is if you go back up to this diagram and you're like, oh, this is 3.1 kilometers, and you just write it in on the picture here. This would be a really good idea there. And I should probably zoom in just so I can make this a touch neater here. So this is gonna be 3.1 kilometers. Perfect. So if you have a diagram, just fill it into that diagram, because then let's say you ended up forgetting that you put a little sentence next to this, it would make it a lot better for the teacher or whoever's looking at this to be like, oh, okay, they're talking about this distance being the 3.1, therefore it's connecting. Now, I would always recommend the sentence, but you know, if it's not in there, at least to have it in the diagram, and that should make things a little bit better. Okay, now that's kind of an applied problem where we take a sentence, we break it apart, we use sine law and triangle sum theory from grade 10 to help us figure this out. Now, if we go to example 2, determine an unknown angle measure. Well, let's say we have some sort of description of a triangle. So in this case, they haven't drawn it for us. They're just going to give us information here. So they say in triangle CAT, where the vertices are CA and T, angle C is 64, the side length C is 25.2, and then in this, there's a bit of a typo. You want to fix this. Instead of C, make this an A here. So side length A is equal to 16.5. then determine the angle of t to the nearest degree. So basically to the nearest whole number. Now, anytime you're given a description of a triangle without actually the visual of it, I just recommend you just throw that thing together. So try not to make this a right angle triangle, or else that's going to confuse you, because in this unit, we don't deal with right angle triangles. And I'm going to try and make this actually connect. There you go. Perfect. Now what we're going to do is we're going to put our vertices together. So I'm going to make this C, A, and T. Not that it really matters, but sometimes if you draw this with a certain way and then the angles are larger or bigger and it doesn't really make sense, you might get thrown off a little bit, but don't worry about it. As long as we have CAT, we're happy here. Now what I'm going to do is on this triangle, I'm going to label the sides. So we have our side length T here, we have our side length A here, and we have our side length C here. And again, they use lowercase letters across from the angle. Now, let's fill in the angles that we know. For this one, they said that the angle at C was 64 degrees, so I'll fill that piece in here. They also said that our side length C is going to be 25.2, so I'm going to make sure I write that in here, 25.2 meters. I'm going to include the units. And then side length A was 16.5. So I'm also going to fill that in here and include the units. Awesome. All right, now, if we want to determine the angle at T, we're missing too much information to directly solve for it. And here's what I mean by that. We have a pairing of these two together. So we have angle C and side length C. That's one pairing. But we don't know anything about T as is. We don't know its angle. We don't know its side length. So what we're going to have to do is we're going to have to solve for angle A first using the sine law with A and C. And then once we have that piece, then what we can do is we can transfer that over and say, using triangle sum theory, we can figure out angle T. So I'm going to start by going step number one. Let's put together the sine law for A and C. Now, if I'm solving for angle A, remember, we can put the sine of A in the numerator with the side length in the denominator. And then for the other side of the equals, again, we have to replicate this, but we're going to put C instead. There we go. Now, we want to isolate this for angle A. And in order to isolate this for angle A, first and foremost, I'm going to surround everything in brackets and multiply everything by A. Now, what this is going to do is it's going to cancel the A from the denominator on the left-hand side and leave me with sine A is equal to A times sine of capital C, because that's the angle of C, divided by side length C. And the reason I'm going to write this A out in front is I don't want it to be like C times A. That sometimes is a little bit confusing, especially when sine is a function of C, or C is a function. I should explain it the right way. Sine is a function of C, so we don't want to have A embedded with C. I like to write it out in front like it is here. Now what we're going to do is, if I want to isolate for angle A, I know that I have to do the inverse of it. So I'm going to go A is equal to inverse sine of the entire ratio of A sine C all over C. Now from here, what I'm going to do is I'm going to write this as A is equal to sine inverse, and we're just going to fill in the information we know. In this situation, side length C was side length A was 16.5 of sine of 64 degrees, which is the angle at C, divided by the side length of C, which is 25.2. In your calculators, as long as you're in degree mode, you'll get A is equal to 36 degrees to the nearest degree. Now, what we're going to do is, as soon as we get information that we can fill into the triangle, I just recommend going up here and being like, okay, 36 degrees. There we go. Now, the angle we're looking for is angle T. To simply wrap this problem up, all we're going to do is use triangle sum theory. We know that if I add these two angles plus T, it gives me 180. So therefore, in our final step, which is going to be step number 2, we're going to say, therefore, angle T, remember using that little inequality. It's not an inequality, but it's just representing the angle, is equal to, we're going to take 180 degrees, and we're just going to subtract away the degrees we know, 64 minus 36, and we're going to get that angle T is equal to 80 degrees. Perfect. And then we can fill that into our triangle. We can highlight that as part of our answer to be like, yep, there's our final solution, and we're happy with this. Now, again, when you draw these triangles, don't be too worried about the scale of these, because when you're hand drawing them and then randomly assigning vertices, you may not accurately portray this. Because if I look at this triangle, I wouldn't say that this angle is less than this angle, but just the way we drew it out, it ended up working out that way. But don't be too bothered by that. As long as you're setting up your vertices and your side lengths in the appropriate way of being angle and then opposite of that angle is its side length, then your diagram can be a little bit inaccurate. Unless it's given to you directly, you might have these inaccuracies pretty much every time. All right, There we go. So there's an example of we don't have a diagram, we draw it out based on description, and we may have to use sine law once, twice, just depends on the situation. Never feel that you can't use triangle sum theory to help you out. That's a really good, powerful tool from Math 10C. I recommend you use that frequently because it's going to help you a lot. Okay, now let's amp up the difficulty just a little bit. We're going to deal with some applications of sine law, and starting off with one that is going to take a bit of work to solve here. Now, two angles in a triangle are measured at 60 and 45. The longest side is 10 centimeters longer than the shortest side. Determine the perimeter of the triangle to the nearest tenth of a centimeter. Now, this one's pretty applied in the sense that we first of all got to draw out the triangle and then label as much as possible. So here's my triangle, nothing too special, it's gonna do the job as long as it's got its three vertices. Oh, it's not gonna let me do this again. Let's see, there we go. Perfect. Okay, now what I'm going to do is I'm just going to throw three random vertices on here because they didn't tell us anything about a specific triangle. So I'm going to go A, B, and then, or actually I'm going to make this one C, and then I'm going to make this one B. Not that it really matters, but we're just going to put them on there. Now, here's what they want us to do is we want to label out some of these degrees automatically. So what I'm going to do is I'm going to label, let's say angle 60 will go here. I'm going to then label 45 degrees, which will be here. That's the other angle. And then we don't know this angle. Angle B was that missing third angle, but we can use triangle sum theory quite easily to get that value. The other thing we want to do is we want to be thinking about what possible labels we could throw on here, but we can't determine which is the shortest and the longest side until we know all the angles. And I'll explain that in just a second, but let's figure out what this other angle is so that we can figure out what missing angle here or what sides are what. So from this situation, we know that by triangle sum theory, and I'm just going to write it as sum theory or sigma theory, we know that 180 is equal to the 45 plus the 60 plus angle B, and I got to have a plus sign in there, plus angle B. Now, angle B, when we subtract away 180 minus 45 and minus 60, we'll end up getting 75 degrees. So in our triangle, we can then go in and fill in the 75 degrees here. Now that we know all the angles, this helps us establish which is the shortest side, which is the longest side, and which is kind of that medium side. So from here, the longest side will always be across from the largest angle. So if this ends up being the largest angle, then its largest side is over here. Because you can think about it. The further lines are spaced apart angle-wise, the greater the line segment that connects the opposite vertices. So in this situation, if the longest side is 10 centimeters longer than the shortest side, then in this situation, let's let the shortest side be defined by the one with the smallest degree, aka C. So I'm going to label this as X. And then the longest side is across from 75. It's going to be X plus 10. And then the medium one, we don't really know what this is. In fact, we're just going to label it as side length A because there's no real description of like how it connects to the other two. It didn't say anything about it being like longer, shorter, whatever else it might be. It just said, hey, you know what? We have a short side and a long side. And then whatever that other side is, we're going to need to figure that out. So first of all, let's make sure that we just say, and you know what, I'm going to actually move this work down just a little bit here so that we can define it right above. Because we've used X as the shortest side, I'm just going to make sure I write that. Let X be the shortest side. Perfect. Just so that we have it defined and then we're not like questioning what's going on here. Okay, so there's step number one. We figured out that secondary angle, which is angle B. And then from angle B here, we now know that we can figure out these other side lengths using the sine law. Now, step number two, I'm just going to bring it down here. We're going to use sine law in order to figure out what one of these possible values are. And what I'm going to do is I'm going to use the pairing of the following. I'm going to use 45 and X. And I'm going to use 75 and X plus 10 as the way to do this. So in this situation, if I'm trying to solve for X, I'm going to go X plus 10 divided by sine at 75, because that's the opposite side or opposite angle, is equal to X, which is the side length of C, divided by sine at that angle of C, which is 45. Perfect. Now, in this situation, what we're going to do is we're going to isolate this for X. In order to isolate this for X, we're just going to cross multiply. So I'm going to take both of these and be like, cross multiply sine 45 up this way, cross multiply sine 75 up this way, and we're actually going to calculate what these values are. So this would look like the following. It's going to be x times sine of 45 plus 10 times sine 45 by distribution property is equal to x times sine of 75. So we cross multiplied it and then we distribute that sine 45 and distribute the sine 75 to each of the sides. Now what this is going to give us is that on the left hand side we're going to end up getting that this is 0.7071x plus 10 times sine 45, which is 7.071, is equal to this x times sine 75, which is the same as 0.9659x. Okay, now I want to isolate this for x, so I'm going to subtract away this x from the one side. I'm going to go minus 0.7071x, and I'm going to bring that over to the other side using subtraction. Continuing this just off to the side here, we end up getting that when I have my x together, it gives me 0.2588x. When I take 9659 minus 0.7071 is equal to, on the other side, whoops, don't want to make sure I undo that, there we go, is equal to 7.071. I'm going to divide both sides by the 0.2588. Excellent. And then this is going to give me that the x value is equal to 27.3. Perfect. Okay, so this is to the nearest tenth, and so I'm going to hold on to that. And when we have this information, you know what I would do is I would highlight this right away and be like, okay, this is an important piece of information, and I'm just going to arrow up that I've continued this way. So this is a continuation of this. I'm going to throw that onto the triangle. This becomes 27.3, and this is centimeters. Perfect. There we go. So you want to make sure you just write it on the triangle as soon as you have it. Now what we have is we have this x, we have an unknown a, we have all three angles. We can figure out this x plus 10 because now that x is 27.3, that means that 27.3 plus 10 is 37.3. So now we have two side lengths, all of the angles. We just need to figure out what this missing side length of a is, and then we can determine the total perimeter by adding them all up. So to determine that, what we're going to use is sine law. And realistically, it doesn't matter if we use B or A at this point, or B or C, I should say, because we know their angles and side lengths. Let's say I use B in pairing with A. So I'm going to go over here and be like, for step number 3, which we're at, there we go. And I'm going to try and generate as much room as I can. For step number 3, we have side length A over sine of A is equal to side length B over sine B. Now, again, for some of you, you might be like, wait a minute, why are we using where the relationship has this side length in the numerator? It's because we're trying to solve for that side length A right here. And so we're going to use this pairing and this pairing in order to figure this out. And we want to solve for A. So let's start with it in the numerator to eliminate some of the algebra. Now, in this situation, I'm going to go multiply by, multiply by. We're going to multiply both sides. And I should probably move this over just a tad to create some space. I'm going to multiply both sides by sine of A. Because when I do that, it's going to eliminate it from the denominator on the left-hand side. And it's going to leave me with side length A is equal to B times sine of A, all divided by sine of B. Now, filling in numbers here, this is going to be equal to side length B, which is 37.3, times sine of A, the angle at A is 60, divided by sine at B, which is 75. And then this is going to give us where A is equal to 33.4. Awesome. So now we have all three of the side lengths. And I would go fill that into your triangle right away. Be like, okay, I have this 33.4. Let's make sure I just write it here, include the units. Now, to calculate perimeter, simply we just add them all together. We use a very rudimentary grade 8, 9, and 10 skill. We just put them all together, add them all up, and sum them together. So I'm going to say in the very bottom with our remaining room, therefore the perimeter is equal to, we're going to take 27.3. We're going to take 37.3, which were the values of our B and C values. And then we're going to add up our A value here, which is 33.4, therefore giving us a total perimeter to the nearest tenth of 98.0 centimeters. Perfect. So that would be our value of our perimeter, and we'd be happy with this piece here. Okay, let's go to our next applied example. So clearly, you can see that we're going to have to use a mix of triangle sum theory, maybe a bit of algebra, and actually computating values of sine at certain points to get missing values, and then using sine law maybe once or twice, just like we've alluded to before, and we can get a value. Now, let's go to example 4, where we have the following situation. There's an airplane that's flying over the town of Mathville, and between two tracking stations, they measure two different angles from two different stations that are measuring this flight pattern over Mathville here. So station 1, which is on the ground somewhere, let's create a triangle, a non-right angle triangle, just to kind of represent what's going on here. We're going to label the left-hand side as station number 1, or S1. We're then going to label S2 as station number 2, or the vertices over here. And then for our third vertices, I'm going to label this as the airplane up in the air here. Now, they say that it's flying between these two tracking stations. The angle of elevation from station 1 to the plane is 36. So we know that the angle here is 36. They say that the angle of elevation from station 2 to the plane is 48. So I'm going to write 48 here. If the stations are 1,675 meters apart, so if this is 1,675 meters here, then what is the altitude of the plane to the nearest tenth of a meter? Now, here's what they're actually asking for here. They're saying, what is this? What is the height of the plane from the ground? Now, what we've done is we've created two right angle triangles by generating an altitude or generating a height. But in order to figure out what this altitude is, we need to figure out a couple missing pieces here. The first one I'm going to always do is if I know that there's a missing angle in the triangle and I have the other two angles, I recommend using triangle sum theory right away. So I'm going to say right here, we're looking for step number 1 by triangle sum theory, which again, I'm just going to short as sum theory. We can say that 180 degrees, which is all the interior angles of 36 plus 48 plus angle A is equal to 180. And then when we subtract away the 180, or when we take 180 and minus these other two angles, we're going to end up figuring out that angle A is equal to 96 degrees. So I'm just going to fill that in right into the triangle here, that this is 96 degrees. Okay, great. So if we know that this is 96 degrees, that gives us some power in terms of figuring this out, because when we look at this, now this gives us the ability to use the sine law in order to figure out either a side length of S1 or a side length of S2. And I'm going to fill that in the following way. Right here, this is the side length of 2. This is the side length of 1. Because remember, it's opposite of their angles, right? We need to figure out one or the other of these in order to figure out the altitude. Let's say we want to solve for S2 to help us out. If our end goal is to get this height, we need something in the 90-degree triangle that allows us to connect it to this, meaning we need S2. So we're going to use the sine law to get this value here. Now, our pairing is going to be the following. To get S2, we need to pair these two together and these two together, because this means that we have 2 degrees that we know and 1 side length that we know, and then that will allow us to get this unknown side length here. So putting this all together for step number 2, we're going to write this below and be like, step number 2, side length of 2 divided by the angle at 2, which is sine of 48, is equal to 1675, which is the side length of the airplane's side length between the two stations, divided by the sine of that 96 that we just found. What I'm going to do is I'm going to multiply both sides by sine 48. So this will become sine 48 here. That's going to end up eliminating sine 48 from the denominator, leaving me with S2 is equal to 1675 times sine of 48 divided by sine of 96. And again, the reason I put that 1675 or that value in front of the sine function is I don't want to make it look like sine 48 times 1675, because the sine and 48 are directly connected to each other. Now, this is going to give us a value of, in our calculators, 1,251.62 meters. And I'm just going to hold on to a bunch of the decimals just because we're not done the problem yet. It's a good recommendation to do, especially in like other sciences. Just hold on to some numbers here. So 1251.62, and this is in meters. Now what we can do is just do a simple sine function to figure out what the height is, or the altitude, because we know the angle. We know this is a right angle triangle. We have opposite over hypotenuse. opposite over hypotenuse, this is the sine ratio. So we're going to use the sine ratio on this side. And we're going to go for step number 3. Sine of 36 degrees is equal to the altitude or the height above the ground divided by the hypotenuse, which is this 1251.62 in meters. In order to eliminate the 1251 from the denominator, we're going to multiply both sides by 1251.62 meters. There we go. And when we do this, we're going to end up getting that our height is equal to 1251.62 times sine of the 36, and therefore the height or the altitude above the ground to the nearest tenth of a meter is 735.7 meters. There we go. And again, when you have this, highlight it, box it, circle it, whatever you want to do. But I would always recommend, if you have a diagram that goes with it, just fill it in here. So it'd be like, this is 735.7 meters, just so that like it's very visible of what you actually just solved for and what you're indicating is the solution. So interesting problem here, because on top of us having to use triangle sum theory and the new sine law we've discovered, we've also had to go back to math 10, and we've had to look at this idea of using basic sine relationships in order to solve for some piece of a triangle. Just remember that you can only use the basic primary trig ratios if you're talking about it being a right angle triangle. So the reason we were able to do this third step here is because this is a right angle triangle generated by the 90 degree that creates the altitude. If that wasn't true and we wanted to solve for some piece of this triangle, we would have to use either sine law or cosine law when we get there. But for now, we're looking at this and being like, the reason we could do this was because there was a 90 degree angle here. Okay. Now, here's where we get to some more tricky material, and that deals with the ambiguous case, or the ambiguous case of sine law. Now, this occurs in a very specific situation, which we need to do a specific test for to determine how many possible solutions are there given a certain setup. So when we talk about the ambiguous case of sine law, we need to do a bit of an analysis originally. So first and foremost, if you were given measures of 3 sides, side, 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 or 2 sides and an angle, or angles of an angle side angle or angle angle side, then this is uniquely defined. Those are the conditions for congruencies of triangles. So when we're dealing with the sine law, we need to have these possible cases in order to deal with specific situations. And more importantly, when we deal with these first two of side, 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 or side, angle, side, that's actually cosine law. So it's only when we get this situation here, angle, angle, side, or angle, side, angle, that we can deal with the sine law. The other two cases are going to be cosine law, as we're going to deal with in the future. Now, the ambiguous case occurs in the following pattern. If we are given 2 sides and an angle opposite of those sides, so side, side, angle, then the ambiguous case occurs. And again, the ambiguous case occurs when we're given measures of 2 sides and an angle, A and B, and you are given the measure of the angle opposite to the shorter of the 2 sides. So very, very specific conditions, which we'll see throughout the examples here. Now, here's the 3 cases we might encounter. When we're dealing with the ambiguous case of this situation where we have the side angle, here's the possibilities that we're going to deal with. And we're always going to set it up in the same way of vertices so that we can clearly and easily put it together. There will always be one triangle if we have one solution such that the height or the opposite side of A is equal to the direct correlation of that being where this has exactly one solution in the sense of when we do our test, we'll figure out that our opposite side length of A is directly equal to that relationship of A. Now, in the case that we can have no triangle exists in the following situation where there's no solution if that side length of A or the opposite side length is shorter than the theoretical length here, or the theoretical side length that would make it so that it connects to build that triangle, then we say that no matter where this arm goes, either it's left or right down the middle, it will never connect down to this bottom line of the triangle, and therefore there's no solution. There's no possible triangle that can be drawn such that we can use sine law. The last situation, which is 2 distinct triangles where we get 2 distinct solutions, is when we have this idea that the A side length is longer than the theoretical length that would make up this one triangle, and so it can exist in 2 positions. The first position, it can exist to the left creating this triangle that's kind of slim like this. This second case scenario is when we swing it out this way and it can connect over on the right-hand side, and therefore when it connects over on the right-hand side here, it will generate a solution where the triangle is a little bit larger like this, and we have that look. Now, when we look at these here, we're going to flip over and we're going to go through the possible case scenarios in which this can occur so that you can clearly see what we mean by the theoretical height and how we do this test to determine which possible case do we have. Do we have no solutions, one solution, or two solutions? Okay, in this triangle A, B, and C, we have an angle of 125. We have A, which is 27. We have B, which is 14. Now, in this given situation, what I would always recommend you doing is setting it up in the exact same way. And what I mean by that is you want to set up A on your left vertices, C as your tops, B as your other vertices. So I'm going to lay it out in the following manner. I'm going to lay it out where we have A, which is going to be down in our left-hand side. And I'm going to draw it in a very particular way for a specific reason. So I'm going to look at this and be like, if my A is here, here, and here, there we go. And I'm going to put my A right here. I'm going to put C at the top and B over on the other side. Now, according to this, we have that A is 125. So I'm just going to write that in here. This is 125 degrees. Our side length A is 27. So I'm going to fill that into the triangle too. There we go. And then I'm going to put B as 14 centimeters like this. We look at this, and in this situation, if we're given the angle A, and this angle A has it such that this side length of A is greater than the side length of B, where B acts as the swinging arm. And I'm going to label this. This is A, this is B, this is C. B is what we consider to be the swinging arm. This is the one that could potentially exist in two positions. If this situation occurs where we have an A that is greater than the B, this means that this can only exist in one pattern. I can't swing this B arm out to a different position such that it would generate this exact same triangle here. This wouldn't exist in that way. So when we see this, we're just going to simply boil it down to, if we know, therefore, since side length A is greater than B, we say that there is only one solution. Perfect. This is a prime example of there can only be one triangle constructed in this given situation. Now, let's go down to this other one, which we're going to kind of draw like the previous page. This one was a little bit unique in the case that we have a situation like this. If A, B, and C has an angle of 50, a side length of A being 15, and a side length B being 20, then let's lay out the triangle in the following way. I want you to draw the first arm like this. I want you to draw an arm that goes across like this. And then what I want you to do is I want you to draw one that goes straight down here. Now, the reason I'm going to draw this straight down here is I want you to be thinking about it in the following way here. When we allocate this stuff into our triangle, we know that we have our vertices. We're going to always label them in this way with the ambiguous case. A is going to be here, C is going to be the top, and then B is going to be wherever it is or wherever it connects. In this situation, we don't even know if it connects, to be honest. We don't know if there's one solution, zero solutions, or two solutions. So I'm going to leave it as we don't know where B currently sits. Now, we're going to fill in the information that we can, which is the following. We know that this is our side length A, which is 15. It's going to be across here. So this is 15 centimeters. We know that B would be somewhere, wherever this vertices ends up lying, depending on if there's solutions, and its side length would be here. And then the angle A, which is going to go 50, which is here. Now, we have to do a theoretical test to determine if there's actually solutions that go with this. Here's the theoretical test that we're going to do. We're going to use the basic sine law and say sine of 50, or sine from the corner 50, is equal to the height, as we're going to call it, or this measure here. We want to see what the height is actually theoretically, given that this is a 50-degree angle. And then this is going to give us height over the hypotenuse, which is 20. When we multiply both sides by 20, there we go. This is going to give us h is equal to 20 of sine 50. The height is equal to 15.3 centimeters. So the theoretical height that this would actually create in order to have some sort of solution where it connects down here is actually 15.3. And so if this is actually supposed to be 15.3, here's what this looks like. Visually, the actual height looks like this. It would be a line that goes and connects below the triangle. In this situation, or sorry, I should connect it directly to, the actual height is 15.3, and the height that we've actually generated in our problem here is 15. Do you see how this is slightly shorter than what it's actually supposed to be? That means it doesn't actually connect. When we see this, that side length of 15, which is the side length of A, is shorter than it's supposed to be. It's supposed to be 15.3 or greater, and if it's shorter, then this arm never connects to the base of the triangle, and as long as it's swinging backwards and forwards, no matter where it would swing to, it could go a little bit inwards, it could go a little bit outwards, it's never going to connect down to the bottom of the triangle because its theoretical value has to be 15.3 or greater. Therefore, we see this as it being 0.3 shorter than it's supposed to be. So we'll make a note about that. The height, or the 15 centimeters, is short by 0.3 centimeters. Thus, there is no solution. Perfect. And did I highlight the last one? I did. So I'm going to make sure I highlight this one too. So very, very critical. So this is our first situation of seeing the ambiguous case where we're like, oh, if it's shorter than its theoretical height, then it must be that there's no solution because there would be no ability for this arm to connect and create a triangle. Now, let's look at the last case, and we can actually determine that we look at this and be like, okay, well, if we've now dealt with one solution, we've dealt with 0 solutions, you can only imagine where this one's going to go. Let's draw out our triangle here. So again, we're going to draw it always in the same way with the ambiguous case. I'm going to draw my bottom length. We don't really know exactly what it is. I'm going to draw the height, the theoretical height being the part that connects it down here. And then what we're going to do is we're going to label all the things we know. So this is going to be A, C, and then B, we don't really know where it is. We have to kind of leave it as we don't really know where it is because we don't know where this arm is sitting. Is it a direct 90-degree angle? Is it to the left or to the right? We got to figure that out. Now, in this situation, I'm going to fill in the information out. 30 degrees goes here. Side length A is 13 centimeters. So that's supposedly the one that's here. And then 21, which would be across from B, where we don't know where B is currently. It's somewhere down here if there is a solution. We just don't know exactly where. And you'll see us fill that in a second here. Now what we're going to do is we're going to do our theoretical test. The theoretical test says, hey, if we want to figure out what this height is, we need to use the sine law. So we're going to use, or not the sine law, but the basic trig ratio of sine. Sine of 30 is equal to the height divided by the 21. We're going to multiply both sides by 21. There we go. And then so this gives us 21, whoops, I'm going to go back here. Height is equal to 21 sine of 30. There we go. Therefore, the theoretical height that this should be is 10.5 centimeters. And in this situation, here's what we have. They're saying that the theoretical height for this one should be 10, which in this situation, I'm going to write this here, is equal to 10.5. If this is 10.5, then the actual arm that is overlaid here is longer than that situation here. And if it's longer like this, it actually means that it exists in 2 positions here. And maybe the way I should draw it is the following here. I'm going to just backpedal this just a slight bit here, and I'm going to draw that this is the 10.5 centimeters right here. And if we have 13, then we have to rotate it a little bit because 13 overlaid like this would look like this down the middle. It would look like where we have a bob on the end or a connecting piece that goes well below. If it goes beyond this, then we have to rotate it either inwards or outwards in order to establish this. So here's what we're going to do. We're going to write one solution where we rotate it in a little bit to the left, therefore connecting it here and creating one of our solutions. The other solution would be is if we go this way and then we connect it down here and we say that this is solution number 2. And this would be the vertices. This would be B here, and I'll backpedal that just to put it in black. This would be B here, or this would be B here, depending on which solution we're talking about. So this is a situation where if your height that you're given is longer than the theoretical height, well, it's not one solution, it's not no solutions, it's two solutions because it can exist in two different positions. So let's just make sure we note that here. Since the side length of A is less than B, B being this larger swinging arm, and the side length of A is larger than the height, there could be two possible solutions. Perfect. And then the way I'm going to express this just in brackets is two different triangles. Now, when I say this idea of two different triangles, one of those triangles is the slimmer one that looks like this, where the arm rotated left. The other triangle is the larger triangle when it rotates to the right. And this situation is going to generate where we might have to do quite a bit of work. If we're ever given this situation of you wanted to solve the triangle for all possible solutions, it's going to require a bit of work because we're going to use sine law and triangle sum theory for these two different triangles, which is one of the upcoming examples. So I want you to watch out for that because we will be covering that very, very shortly here. Now, let's just make sure we highlight our sentence to indicate that this is our possibilities, and then we'll move on. Now, again, most important thing, we want to do the test every time. Okay, let's cycle over to this problem here. So this is going to deal with using the ambiguous case. And first of all, we got to figure out how many possible solutions there are for this triangle. So again, I would always recommend you draw some sort of very simple diagram here. So I'm just going to draw it out like this, draw out my base value, and then just draw some sort of arbitrary height in here. And then what we're going to do is label our vertices just as we've done before. So A, C, and then we don't know where B is. So we kind of just have to let that sit for a second. We're going to fill in as much information as we can. So this is 39 degrees. The opposite side is going to be 10 centimeters apparently, and then this one is going to be our 14 centimeters apparently. Now again, we don't really know where B is because we don't know how many solutions there are. There could be one, there could be two, there could be none. So we got to figure that out. In step number one, you always want to do your quick theoretical test and say, okay, well, to do the theoretical test, we take the sine of 39, which is equal to the height, the height that we're trying to figure out. We're trying to figure out if this height is less or greater than, we say the height divided by the 14. We're going to multiply both sides by 14. When we multiply both sides by 14, we're going to get that the height is equal to 14 times sine of 39 degrees. There we go. And then in this situation, we end up getting the height is 8.81 centimeters. And if this is 8.81 centimeters, that means that there's two triangles because B is greater than the height. And so we're going to get this arm that can rotate backwards and forwards here. And so let's just summarize that here. Two triangles. Because B is greater than the height. Okay, there we go. I'll just make sure that's a little neater there. Okay, awesome. So we've done our test. We figured out that our side length is greater. So here's the two triangles that could be generated out of this situation. Again, I'll just do a rough overlay on our first diagram. We could either have this situation with a narrower triangle as the first part. So this would be B, or we could have a wider triangle that goes out and swings to the right-hand side here, and this would create the larger triangle. Sketching these off to the side, here's what we're going to do. We're going to draw our first situation that looks something like this, and we're going to put our vertices in of A, C, and B. And then we have our other triangle, which is that wider triangle. It's the one where we swing the arm out to the right-hand side, and again, we're going to fill in these vertices of A, C, and B. Okay, now I'm going to call it case 1 for this triangle, and then I'm going to call this one case number 2, just so that we have it organized and it's like, okay, which one are we talking about for which situation? Okay, in the bottom left-hand side, we're going to write 39 degrees, as we know, for both of them. For the B value, we're going to make sure that we write this in as 14 for both, so it's going to be 14 centimeters here, 14 centimeters here. And then for the A side length, we're going to write 10 centimeters for both of them because we know that that swinging arm of A is going to be 10 centimeters in both positions here. Okay, now in order to figure out the information here, or in order to solve this, because when they say this key word in this problem of solve A, B, and C, they're saying that for all possible cases, or for case 1 and case 2, what are all the side lengths and all the angles? So I'm just going to indicate some missing information here, and then we're going to fill that in as we go. In the missing information that we need angle C, angle B, and side length of C. We need side length C, angle B, angle C. So we need those 6 pieces of information if we want to figure out all of the relevant information and solve these triangles. And again, as we do the problem solving here, we're just going to start filling it into the triangle. So let's move on to our step 2 and onwards. We're going to start solving for some of the information. And with both these triangles, it looks like I have to use sine law right away. Maybe I do the first triangle, which would be actually, it doesn't really matter which one we start solving with. Maybe we start solving on the smaller triangle. So if we start solving on the smaller triangle, and I'm going to try and keep it all like in the same kind of region. I don't even know if this is possible for it. Yeah, let's see if we can do this here. So below the thinner triangle, I'm going to do all the information or all the solving below this thinner triangle. And then to the right of it, I'll do all the solving for the bigger triangle. So below the smaller triangle here, let's use sine law. And we're going to do this pairing with this pairing in order to solve for B. So to do that, here's what we're going to do. We're going to write it as sine of B is equal to, or sine of B over B is equal to sine of A over A. Okay, now let's fill in the information we know. It's sine of B, which we're trying to figure out, is equal to, we're going to multiply B up and make this sine of A times B over A. Now, we're going to inverse this. B is equal to sine inverse of B times sine A all over A. And then I'm just going to fill in the information. B is equal to sine inverse divided by side length B is 14 times sine A, which is 39, divided by side length A, which is 10. When I plug this into my calculator in degree mode, I'm going to end up figuring out that this angle is going to be 118 degrees. Awesome. Okay, so I want to highlight this piece of information and I want to go back and fill it immediately into the triangle, because the faster I can fill that into the triangle, the better it's going to be for me here. So I'm going to look at this and go back up, and maybe I'll write it in red just to make sure that we're filling in all the new information this way. Okay, so now we know 39 degrees, 118 degrees, and for angle C, we can actually just do triangle sum theory. This one's easy now. So I'm going to take this 118 and I'm going to be like, well, angle C, whoops, not angle A, angle C is equal to, we're going to take the 180 degrees, which is the total interior angle, minus 118 minus the 39 that we knew. And this is going to give us angle C is equal to 23 degrees. Perfect. And again, you want to just highlight that piece of information, and we're going to immediately translate it into the triangle here. So this is going to be 23 degrees. And hey, look at that. We've solved this triangle, but what else are we missing? Actually, we haven't solved it. We need the side length C. So we're going to have to use sine law one time to figure out what this side length is, because we can't use Pythag. If it's not a right angle triangle, no Pythag can be used. Now, we can use any sort of combination to help us out with this. Because we're looking for C, maybe I pair it with, I don't know, let's say we pair it with B. Why not? So we're going to use this pairing and then this pairing to help us out. In this situation, because we're solving for side length C, I'm going to write it as the following. We're going to say that C, or little c, divided by sine of C is equal to little b over sine of B. To solve for C, we're going to multiply up the sine C. So I'm going to go multiply by sine C to both sides. It's going to cancel from the denominator here. We get C is equal to B times sine of C all over sine of B. There we go. Now we're going to fill this in as C is equal to the side length, which is 14 times sine of 23 divided by sine of 118. And this will give us a side length C equal to 6 centimeters when rounded to the nearest whole value. Awesome, 6 centimeters. So let's go fill that in up at the triangle here. So this is going to be 6 centimeters. And once I have my 6 centimeters, perfect. Now we've solved the triangle, because do you see how I solved for all 3 angles and all 3 side lengths? As soon as you have that, you're like, okay, boom, case number 1 is taken care of. Now what we want to do is we want to do the exact same type of information, but for our secondary case, or for case number 2. Now, I'll tell you something really nice about ambiguous case is if you know this angle, you actually automatically know what this angle is very easily. And here's why. If you know that this is 118, the angle that makes up the other case is the complement angle. It's the angle that exists here. If we know that 180 degrees is a flat line and 118 is already taken care of, then the other piece, which is here, is actually the angle that would go right here to fill out the rest of the 180. So what I'm going to do is, simply put, to get that angle B, I'm just going to take 180 and subtract 118. So we're going to go 180, and maybe I'll write it this way. Angle B is equal to 180 minus 118. When we do this, we're going to get an angle B equal to 62 degrees. And I can immediately go back to my triangle and fill that in. It's the complement angle to 118. Just automatically be thinking about that. Anytime you have this two triangle situation or this case one, case two, be thinking that this is where you got to go with this. Okay, now we have two angles. In order to solve for the third angle, let's use triangle sum theory. Keep it simple. We're going to say that angle C is equal to 180 degrees minus 62 degrees minus 118 degrees. Because these are not minus 118, minus 39. That's the other one. There we go. Now, angle C is going to be equal to 180 minus these other two. We end up getting that this is going to be 79 degrees. Awesome. And what I'm going to do is I'm going to highlight this information too, just so that as we're going through this and we're filling it into the triangles, we're not getting confused of like where this information is coming from. So 79 degrees. There we go. And then lastly, we just need to solve for side length C. We're going to use sine law again, just to figure this out and see what we get for the side length of this. So let's pair it with, it could be A or B. In this situation, maybe we use B again. So we're going to use this pairing and this pairing. In this situation, I'm going to write it as side length of C is equal to, side length of C divided by sine of C is equal to B over the sine of B. There we go. We're going to multiply up this sine C just as we've done before. Ooh, it's a little squishy here. I'm going to try to squeeze that in there. Sine of C. There we go. It's going to cancel from my left here. This is going to be C is equal to B times sine of C all over sine B. And then we're going to get that C is equal to B, which is 14, times sine of C. The angle at C was 79 degrees. And then we have our sine of 62, which was our angle B. And just to confirm, yeah, 62. When we plug this into our calculator to the nearest whole number, we get 16 centimeters. Perfect. Okay, now I'm going to make sure that's just a little bit straighter there. Perfect. We're going to go back up to our triangle and we're going to write this in. So we're writing in 16 to our triangle, 16 centimeters. Perfect. And now, do you see how both triangles have all three angles and all three sides? Therefore, you've done what they've asked and you've solved for the ABC triangle for all possible cases. And the other instruction that I kind of ignored, but I just did throughout the problem, is we answered all of our answers to the nearest whole number. Just make sure that you're looking at that before you start your problem. You want to make sure that you're answering this to whatever they ask for. So they could say a tenth or a whole number or a hundredth, whatever it might be, you want to be following that instruction. All right, now with the ambiguous case, there it is. There's probably the hardest problem you would deal with the ambiguous case. Look at how much work there is. We had to deal with triangle sum theory. We had to deal with the sine law in multiple cases. We even had to use the complement angles within saying, hey, you know what, if we're solving for some angles, we actually can relate case 1 and 2 for these bottom angles of B there. That's one part that came up. But where this all stems from is you must do your test. And the reason you must do the test is, again, because you might be given a situation where you don't know how many solutions there are. And if you don't know how many solutions there are, then how do you know what type of information they might ask you for? Because they might ask you for an angle or a side length from case 1 or case 2, and you won't know unless you do this case analysis. So automatically, I highly recommend set up your triangle where A is in the bottom left, C is in the top, and then B, you don't know yet until you do your test. To do the test, we're going to use the basic primary trig ratio of sine and say, well, the theoretical height that is opposite of the angle A should be equal to whatever this h over 14 is. We do h over 14. we multiply whatever that hypotenuse is out of the denominator, and as soon as you know that your height or your theoretical height is less than the given value, that essentially means that this 10 extends beyond that height that you're given, so it can only exist if you rotate it to the left or rotate it to the right. If you don't rotate it to the left or to the right, the arm would look like this, and that's not a triangle because it goes beyond the given base of the triangle. And yeah, I guess theoretically you could say, oh, well, it still creates a triangle, but does it really? Because this implies if it's 10 centimeters, the vertices of C is down here, and if the vertices of C is here, that means that there's no triangle created. It has to or angle, or I should say the vertices of B. The vertices of B would be down below here. And if it's down below here, the only way you could create a triangle is to rotate it inwards such that it connects to the base, or rotate it to the right such that it connects to the base. All right. Again, probably one of the most difficult problems in our notes today, but I know that once you kind of get the swing of it and the rhythm of it, and you can do that initial test to figure out how many solutions you have, it will make this all very apparent, and you'll probably do very well with this. Now, again, this is where you're going to want to go on to the practice. Here's your assignment from the textbook. I'll probably even have some additional handouts for you in terms of notes, or just little pointers that I can give you in terms of the sine law and just dealing with the ambiguous case. But make sure you're trying out a couple practice problems on your own, because it is some difficult material. All right, good luck with your practice.